Welcome, everybody. It's my pleasure today to introduce Fedor Manin, and he'll be telling us about linear null homotopies of maps to spheres.
Thanks a lot for the introduction and the invitation. This is a topic that I've talked about a lot, and this particular talk is pretty much identical to one I gave at Penn State almost more than a year ago, and so hopefully it'll reach some people who haven't heard it yet. But what I want to talk about is goes back to stuff that Gromov was thinking about pretty intensely in the 90s. So turns out in 1996, Princeton had this conference called Prospects in Mathematics, where all these famous people were supposed to talk about what the next big thing in their field is. And Gromov gave this talk about quantitative homotopy theory. In the past few years, several of us, I'll list names later, have sort of been realizing the vision from that talk. And the thing I want to start with is a sort of silly idea where here's me. I'm looking in a telescope, and somewhere many light years away, I see myself. And so that tells us there's some sort of closed geodesic loop in the universe, and we want to know whether the universe is simply connected. So is this geodesic loop actually essential, or is it contractible? And I don't really know how to test that experimentally, but you could sort of try to find a contraction for this loop. But then, says Gromov, suppose somehow it turns out that the loop is contractible, but the amount of time it actually takes to do this contraction takes longer than the heat death of the universe. Is it really contractible at that point? Or like, do we really care that it's contractible? Or for all intents and purposes, is it an essential loop? So somehow this tells us that even when we're never, in real life, we're never thinking purely topologically. There's always some geometry involved. And people who think about topological data analysis obviously also have the same perspective, right? The topology is not absolute. It sort of arises from your geometry. And so now I want to focus for a bit, right? Like, how could this sort of thing happen? How could you have such a contractible loop that's extremely hard to contract? And there's a sort of stupid way you could do it, which is you could have this dumbbell with a really thin neck, and then the loop in that thin neck, you have to go through the whole dumbbell to contract it. But this is sort of the reason this is stupid is you're only making use of geometric data, right? This is still a sphere, and you're just making the scale of the geometric, the scale of its geometry much smaller than its diameter, and then you can do all sorts of things. But what if you're not allowed to do that? So here's another kind of example. Take a manifold with undecidable word problem in the fundamental group. And it turns out you can actually make this manifold a homology 5 sphere. So this means its homology is the same as that of S5. And right, then there is some, right, take a curve in this manifold, a loop in this manifold that you know is contractible, then there's some bound in terms of its length on how big a contraction is. And that's basically just because up to little perturbations, there's only finitely many such loops of length L. So there is some filling area, or Dane function, as it's also called. By a kind of compactness argument. But this filling area function is not bounded by any computable function of the length. So it's some function, it grows extremely fast, faster than any tower of exponentials, than the Ackermann function, whatever function you can actually write down, it grows faster than that. So why, this is not too hard to explain. Basically, if you did have a computable bound, then I said that there's only really up to small perturbations, finitely many loops with that of at most that length. And so you could, or sorry, in this case, disks of at most that area. And so you could go through all the possible disks that might be fillings of your loop, and either there will be a filling or there won't be a filling, and that will tell you whether the loop is contractible, and that will tell you whether the corresponding element of the fundamental group is trivial, which is a contradiction because we said that the word problem was undecidable. So these sorts of things where computability theory ends up playing a role in the geometry of the space. A lot of that occurs in work of Alex Nepotofsky, and there's a whole super interesting theory, but it's not quite what I want to talk about. This is really sort of a preamble to show that the results I am going to be talking about are non-trivial. And so I'm going to eliminate the fundamental group completely from my story, and I'm going to take a simply connected target space. And does that make our life easier? Yes, a lot easier. And in fact, sort of similar questions for simply connected spaces always end up giving you polynomial bounds. So here's a specific theorem. If our y is a sphere with some fixed metric, and x is right now thinking about loops in the sphere with the round metric is not very interesting, but let's take any finite simplicial complex. Then any map from that simplicial complex to my sphere, that's L Lipschitz, has an linear in L Lipschitz null homotopy. So I had to replace my notion of size, right? In this one-dimensional version, I was talking about length and area, and it doesn't make sense to talk about something like length for this map, but we end up talking about the Lipschitz constant. And I'll say a bit about what the Lipschitz constant is in a moment. Here's a short bibliography. So this started with this paper with Greg Chambers, Dominic Dotterrer, and Shmuel Weinberger, where we only handled the odd dimensional spheres. And then in this paper, we got a worse than linear bound for even dimensional spheres. Then Larry Guth wrote this very nice survey that was slightly more, he sort of recast our results in a way that let me generalize them a lot. And so there's a lot in this paper, but in particular, the thing that's relevant to this theorem is I improved the bound for even dimensional spheres from quadratic to like almost linear. And then Sasha Berdnikov found a way to make it actually linear for S3 to S2. And then Sasha and I joined forces. And in this paper, again, among various other things, we showed actual linearity for even dimensional spheres. So this theorem was really obtained by successive approximations somehow. Oh yeah, another thing I wanted to say is there's this constant here, right, which implicitly somehow depends on this metric on the sphere, and sort of, again, for Alex Nabutovsky reasons, this constant is going to be uncomputably large in terms of the geometry of this metric. Sort of, you can concoct metrics on Sn, on S5, say that don't look, that are sort of compact and not too, right? You can sort of patch them together out of not too many round balls, but then they look indistinguishable from a space like this. And so up to some point, right, you can find loops that are very hard to fill, for example.
Yeah, so can you say a little bit about the metric on the simplicial complex X? Is it sort of any metric that agrees with the topology, or is it?
Yeah, it can be any metric that agrees with the topology. And I guess one sort of thing that will become clear once I start talking a bit about proofs is that if you sort of make it out of standard simplices, then the result doesn't really depend on the on what X exactly is, but really only on its dimension.
Thanks.
Yeah, so Lipschitz constants, I think probably most people here are pretty familiar with them, but let me just say, right, it's some sort of measure of stretching done by the map. So if you look at points X and X prime in the domain, then if the Lipschitz constant is L, that means you're multiplying the distance by at most L. So this is sort of the standard way to think about it, but I'm going to think about it a little bit differently, just as a matter of perspective. Instead of thinking about maps on the same space with the same metric, but with different Lipschitz constants, I'm going to expand my domain until the Lipschitz constant is 1. And then I can really think about one Lipschitz maps as being locally, they can only behave so many different ways. So for example, right, if this X is a simplicial complex, then after we do this rescaling, let's say that all the simplices have side length 1. Right after I rescale, I can take my simplices and subdivide them in a nice way so that the resulting little simplices have side length, well, maybe not exactly 1, but it turns out you can do always 1 or square root of 2 for every side, some kind of bounded situation. So this turns the complex X into a complex XL. So this is a piece of notation that I'm going to use again. And right, so now if I have a one Lipschitz map from this to some y, then I can sort of move everything a little bit. So a short homotopy is where points move by at most some constant, and my constant is going to depend on n and y. And so you can wiggle things a little bit until the behaviors of your map on simplices come from some finite set of possible behaviors. So we've gone from this sort of analytic definition of the Lipschitz constant to really something with a certain Lipschitz constant as something that once you wiggle it a bit on a certain scale is built out of a finite set of Legos. And of course, one example would be if y is also a simplicial complex, then you get a simplicial map. But that's sort of maybe not the main example. And so I want to give a couple of examples to see, to show you how I want to think of these things. So maps from S2 to S2, right? So take a map from S2 to S2, and I want to say, what does it look like? Or maybe not exactly what does it look like, but what do its friends look like? What do the things that are similar to it look like? And so first I'm going to, and my S2s, let's say, are just boundaries of the tetrahedron. And so then I take that tetrahedron boundary and subdivide it like this. And then I take a simplicial approximation. And so what that looks like is right, each simplex in the subdivision goes to some one of these four possibilities. And now what I want to do this is post-compose this simplicial approximation with the map that takes three of those four simplices and just pushes them down to the base point, and then pulls the remaining simplex over everything. And so what I end up with is, after that, is right, a lot of the simplices, the ones that after the simplicial approximation were mapping to these three, end up mapping to the base point. And then the remaining ones map to over the whole sphere with degree plus or minus 1. So that's sort of, right, those are the Legos that I want to build this kind of map out of. Just maps of maps on cells of degree 0 or plus or minus 1. So here the one skeleton maps the base point, and the two cells map with these possible degrees. And then, right, if you do S3 to S2, you can do very much the same process. And at the end, right, the simplices, the three simplices go to either the base point or to something like this, right, where here's my three simplex, this stuff goes to the base point, and then sort of before we applied this post composition, right, maybe these vertices went to, right, here are my vertices 1, 2, 3, and 0. And so if you sort of think about what happens when you take simplices like this and push them together, right, you get these sort of snakes or noodles inside your three sphere, where the outside of the noodles maps the base point, and the inside of the noodles, the cross section maps over the two sphere with some, right, so implicitly there's some kind of framing inside these noodles. Okay, any questions so far? Okay, so now I want to tell you a little bit about how to use this technology to build nice Lipschitz maps based on some topological data. So if I even get to homotopies, but before I attempt to talk about homotopies, I want to give you this sort of warm-up theorem, because really you should think of a homotopy as a relative map, right? You have some map on the ends of X cross the interval, and you want to extend it to the rest of the interval. But I want to first tell you about a non-relative version. So my target is still going to be a sphere. X is going to be just some finite simplicial complex, and let's say either n is odd or the dimension is at most 2n minus 2. This is about avoiding Hopf invariance. And then I take some homotopy class of maps from this X to the sphere. And there's a way to measure the size of this homotopy class that's sort of purely, why is this alpha? I don't know what alpha is. This should be phi. Right, the comass is a sort of way of measuring the size of this homotopy class that's purely cohomological. So it's sort of you take the fundamental cohomology class of your sphere and you pull it back to X, you get some cohomology class in Hn, let's say with R coefficients, because now I want to think about differential forms. And so I look at all the differential forms that could represent that cohomology class, and I take the one that that has sort of the least local complexity. So this is, what is this comass? It's the infimum of the infinity norm of a differential form. So this is just like its sup value on orthonormal n frames in the tangent space to X, which has a metric, right? And I guess I should say this is a simplicial complex, not necessarily manifold. That's okay. You can still think about differential forms on it. It's really not a problem. Right. So the inf over all the differential forms representing this pullback class. And so I take this comass, I take it to the 1 over n, and that's roughly the scale that I need to expand to in order to build my map, right? So then there's a map in that homotopy class whose Lipschitz constant is linear in this number, in this scale. And sort of why is this the right estimate? For one, it's sharp up to a multiplicative constant. So if we look at, right, there's a particular form that we can get by pulling back the volume form along our map. Right, if you think about, right, pushing vectors forward multiplies their lengths by the Lipschitz constant. So pulling forms back multiplies their infinity norm by the Lipschitz constant to the dimension. And so the pullback of the volume form, its infinity norm is going to be at most a constant times the Lipschitz constant to the n, right? This is just a fixed form. And so the comass is bounded by this. And so this is actually a sharp estimate up to a multiplicative constant. So this is, right, the philosophy here is that the differential form really sort of tells you how to build your map, and you just need to make sure that at the scale at which you're building your map, that differential form is uniformly bounded. So let me tell you why the differential form tells you how to build the map. So the way this proof goes is you take some map in this homotopy class, which maybe has terrible geometry, and you sort of pull it skeleton by skeleton to a nice map. And so at the kth stage, we get a map which behaves nicely on the k skeleton and terribly everywhere else. And what I mean by nicely is, again, it's one of a finite number of possible Lego pieces. right, so the first n-1 stages are trivial. You can just contract, you can take the whole n-1 skeleton and contract it down to the base point. And that gets us a map Fn-1. And now stage n is the hard part. So we want, right, we want on every n simplex to get one of a finite number of maps. Right now we have some map that's that takes the n-1 skeleton to the base point, but could map the n cells with some terrible degree over the sphere. And so somehow we need to fix that. We need to find a homotopy so that we can actually decrease this degree, which means that it has to do something not just to the n skeleton, but also to the n-1 skeleton. So now we can define two forms. One is sort of this almost optimal representative of our homology, of our cohomology class, which we're assuming exists. And the other one is the actual pullback of the volume form. And the thing to notice about these two forms is that they're in the same cohomology class. So their difference is going to be an exact form. So there's some n-1 form whose boundary is their difference. And that n-1 form is going to roughly tell us what to do with how to homotope on the n-1 simplices. So, of course, a form can't exactly do that. So we sort of just take the nearest integer approximation. Right, so when we integrate this alpha over n-1 simplices, we get some numbers and just take the nearest integer to those numbers. That gives us some integral cochain. And then we can define a homotopy, right? So this picture here is of an n simplex across the interval, right? It's a little prism. On this side, we have Fn-1. On this side, we want to have our Fn. And what we do, so the n-1 skeleton of this prism goes to the base point. And then these rectangular n cells, these sort of n-1 simplices across the interval, we just take some map of degree determined by this this cochain A, and it doesn't matter what it is. And so, right, the sort of by since the whole top has to have the same homotopy class as the bottom, right? That means that the degree on the bottom is determined by this formula, which is, right, it's not quite the same thing as d alpha minus the integral of omega, but right, it's pretty close. So there's some n+1 errors that we get from taking the nearest integer. But this is, right, this is bounded. This is at most like about n/2. And so that gives us a finite number of possible degrees. of Fn on the n simplices. And so for each of those degrees, just fix some map of that degree. And have that be Fn on n simplices that are associated with that number. And then again, on higher skeleton, we can do whatever. Right, so now we've achieved a map that's controlled on the n-1 skeleton, on the n skeleton, still uncontrolled on higher skeleton. But it turns out higher skeleton are not too bad. So now we're trying to do step k. K is at least n+1. So for each k simplex sigma, by induction, there's a finite number of things that can happen on its boundary. Also, pi k of Sn is finite. So, right, once you know what's happening on the boundary, the sort of homotopy, the relative homotopy classes of what happens on the interior, there are finitely many of them. And so now for each combination of this and this, just pick a Lipschitz map that realizes it, and those are your finitely many Lego pieces. And so, right, what we did here, in order to produce something that's L Lipschitz, or constant times L Lipschitz, we produce something that's that has a constant Lipschitz constant, a uniformly bounded Lipschitz constant on this the scaled and subdivided complex.
And Fedja, when you say that pi k of Sn is finite, this is where you're using, the assumption that k is sufficiently small, or that n is
exactly
odd.
Yeah. This is where I'm using this assumption. This is where I'm trying really hard to avoid Hopf invariance. And when you introduce Hopf invariance, right, what changes is this. Right, instead of just one differential form, you have a whole algebra of differential forms that you have to deal with. So let me, this is about my allotted time, but I'm going to very quickly run through sort of what would have been the rest of the talk, and then you can later ask me to expand on whatever of those things sound interesting. So basically, right, this was a warm-up theorem. And now I want to talk about how you modify it to say some other things. So first of all, right, to get to null homotopies or to homotopies in general, you need a relative version. So right now, in addition to this complex, you've got a subcomplex. And this is just how you modify the assumptions to get the result that your map on the subcomplex can be extended in a nice way to a map on the whole thing. So you, right, so this is going to depend on having a Lipschitz constant on the map on the subcomplex, and also having some nice geometric data on the rest of the space. And then you can apply that to get the result for null homotopies. And I've traced it out here for the simple case where the domain is also a sphere. And then, then I wanted to say a little bit about what you do for other target spaces that have more rational topology. And so there, instead of just this one differential form, there's this finitely generated in the appropriate dimensions algebra, and a homomorphism to differential forms. Then, you sort of have a controlled homomorphism and an uncontrolled map, and then you use those two things to gradually homotope the uncontrolled map to a controlled map. So yeah, that was probably totally useless, but I'll stop there.
Great. So before we get to questions, let's briefly unmute yourself and applaud for the speaker. And please, what questions do we have? So I'll start with one. How do your results relate to results? I mean, maybe they don't exist or they can't exist along the lines of you have a map, an L Lipschitz map that's not null homotopic, but maybe it's homotopic to another L Lipschitz map. Do your results sort of imply things along those lines, or are questions along those lines potentially within reach, or are they very difficult? Or
yeah, so for spheres, it's really the same. Or for when the target is a sphere, it's really the same story, because you can sort of take your two ends and put them both on one end, and then null homotope that.
I see.
But in general, that's an interesting question, and it turns out there's a distinction, right? So this is what I just said is if you have maps from a sphere, right? Then you can sort of interpret that, right? If you're looking at maps from a sphere, you can add them together. And so there's no difference between homotopies and null homotopies, but even already for maps to a sphere, right? Null homotopies of maps to a sphere are always linear. And there's an example, if you take this product and S3 cross S4 and map it to S4, they're maps which are homotopic, but don't have a linear homotopy between them. But in that situation, I can give you a polynomial, but I don't know anything about the degree of that polynomial in general. So that's one of the results in this paper.
More questions? I want to ask one thing about the history. So am I correct that the differential form perspective wasn't really introduced until, a couple papers in? Is that right? And if so, or was that from the very beginning?
Yeah, I think maybe it didn't come from the very beginning, but it really sort of simplifies things a lot, because we were trying to work with simplicial cochains, but those don't have commutative multiplication, and so that that just introduces a lot of issues. And so it turned out that it's easier to just think about differential forms, and then you end up with these errors when you integrate them and take the nearest integer, but that's something that's not too hard to deal with.
Any final questions? Well, if not, thanks so much, Fedya, and let me stop the recording here.